Welcome, everyone. My name's Nabila, and I'm a graph neural network stream owner here at ACE. For those of you that are new, ACE is a global community of machine learning practitioners, researchers that have gathered around topics in AI research, engineering, and products. Today, we're currently working on creating a repository of authors talking about their research on YouTube, because with all the new papers that are coming out every day, it's pretty hard to figure out what to pay attention to and how to stay on top of things. So our hope with these sessions is to make that process just a little bit easier for you by highlighting papers to our spotlights that we think the community might be interested in on a broader scale. So we host free live sessions just like this one 3 to 5 times a week, but we also produce premium content that we deliver in workshop format. So today I'm super excited to be joined by Joey Bose. He is a second-year PhD student at the RRL lab at McGill/Mila under the supervision of Dr. Will Hamilton. His research interests are at the intersection of graph representation learning, generative modeling, and adversarial machine learning, with a current emphasis on structural latent spaces. Previously, he completed his bachelor's and his master's degrees from U of T, working on adversarial attacks against face detection. He was also the president and CEO of the now acquired FaceShield Inc. This was an educational platform for digital privacy of facial data. His work has been featured on Forbes, CBC, VentureBee, and other media outlets, and is generously supported by IVADO PhD Fellowship. We're super excited to have Joey on this session. For those of you that are GNN enthusiasts, you might already know this, but Prof. Hamilton is the main author of GraphSage, and he really got the ball rolling in this field. So we're super glad that Joey is here and he's been able to learn from him. So today, Joey is presenting a paper that he worked on when he was an intern at Uber AI just last year. He is the first author on that paper, and so he can give us the nitty-gritty details about it. I thought MetaGraph was a cool paper to share today, so that's the paper he's presenting. And I thought it was pretty cool because it highlights this idea of link prediction, but in a more real-world setting. So link prediction is one of those canonical tasks in the graph space where we try to predict the likelihood of an edge between any two given nodes. And this can help out in social networks. So when you're trying to predict if any two given people, which can be represented as nodes, have a relationship between them, like could they be friends, that sort of thing, we can use link prediction for that. But this becomes challenging when we have real-world data that isn't as dense as we would like it to be. It's hard to connect data and get those relationships to train on. And so in all reality, we have sparse data to work with. So traditional link prediction algorithms don't work so well on this sort of problem. And so what's cool about this paper is that Joey and his co-authors decided to approach this problem from a meta-learning perspective. For those of you that didn't know this, like myself is included, meta-learning is the idea of learning how to learn. And so they enforce this into their model, which makes it better at making predictions on sparse data. And so that's what we're going to hear about today. If you're a regular at these events, you'll know that we usually do this kind of in a conference style, where the author will be presenting their paper and for like about 20, 30 minutes, and we do a Q&A after. But today we're trying out something a little bit different. The author is going for a 15-minute presentation with a hard stop at 20 minutes, and he will be uninterrupted. But after that, we're going to do a deep dive into the paper specifics. So for the remainder of the hour, I encourage you guys to post your questions on our YouTube chat, our Facebook chat, LinkedIn, even Slack if you're more comfortable there. And I'll relay them to Joey when we do our discussion after his presentation. Any feedback you have on this new format is really appreciated. We're just trying to make things more digestible for the audience, and we hope you enjoy it. So enough of me, over to you, Joey. We're super excited to have you talk about MetaGraph.
Hey, thanks, Nabila, for having me, and thanks for those kind words. Yeah, so MetaGraph, as you mentioned, was a product of my internship last year at Uber AI. So this is joint work with my incredible co-authors, Ankit Jain, Piero Molino, and obviously my supervisor, Will Hamilton. So I think in the interest of time, I'll get straight into the presentation, and I hope my internet connection is stable enough so we don't accidentally have dropouts. But without further ado, let's get started. Okay, so when we talk about graph embedding, so we're generally talking about this idea where we want to learn representations of nodes and sometimes edges of graphs within a graph. And typically what you do is that you learn these representations through some encoding functions, typically using like neural networks. And the idea is that similar nodes will aggregate in similar areas of the embedding space. And you can use this knowledge to make sometimes useful link prediction, or even other things such as representations and visualizing these node representations. So graph embeddings in general have a variety of use cases, but in this talk, we'll focus on how do we learn effective representations for the task of link prediction, which I'll get into. So as I mentioned, graph embeddings are used for many different problems. One of them is link prediction. The other one also is something like node classification, where you want to maybe classify the label of a node. So for example, in a social network, a label could be yourself or a friend, or maybe you're part of a different community, or in the recommender system setting, maybe the recommendation could be, in the case of Netflix, the type of movie you want to watch. So there's multiple different applications for these graph embeddings. But for now, we'll focus on the first one. So as I mentioned, node classification is this canonical problem. And the problem that we're focusing is on link prediction, which is, simply put, during training, you're given a small subset of a dense graph. And the goal of learning these representation is that eventually you want to be able to predict missing edges or missing links in the overall graph. And this has a variety of real-world use cases. For example, recommending new friends in a social network, recommending new movies to users, or even if you consider knowledge graphs, which are known to be incomplete, you want to recommend, or you want to complete missing facts between entities in a knowledge graph. So suffice to say, there's many actual real-world use cases for doing effective link prediction. So what is this idea of few-shot link prediction? So typically in real-world use cases, you don't really know how dense of a graph that you usually have. And oftentimes, what you do instead have is you have a small, sparse subset of a true graph. So this is actually motivated by a real-world use case. Specifically, as this work was originally done at Uber, that they actually had a particular use case in mind. Specifically, they were interested in understanding how Uber Eats graphs evolves in different cities. So if you think about it, Uber Eats can be thought of as a graph problem as well, where you have users who are using the app and restaurants that are providing a service. So if you order from a restaurant, that's considered like a link. Now, you can imagine that there's some underlying structure within this graph that is shared between cities. For example, if I like, I don't know, Indian food in New York, I'll probably like Indian food in Toronto. So there's this underlying assumption that there's similar graph structures that are shared across cities. Now, the problem arises is basically if I want to deploy this new service in a new city, I have very little information about that graph structure. So because I have very little data on that new city. So how do I make effective recommendations in this setting? So this falls into this idea of few-shot link prediction, where you only have few sets of edges and nodes, but you know that this graph that you're observing is coming from possibly a bigger, denser graph, or maybe even additional previous graphs that are very similar in structure. And another domain, for example, you can think of it as, for instance, in biological networks. If you have, say, protein-protein interaction networks, you know that each interaction graph is coming from some chemical process, and that chemical process is typically the same, even though you have multiple different graphs arising from that. So you know that there's some inherent domain that's guiding the generation process. And because of this, we want to leverage similar structures across different graphs and then do effective link prediction on a new graph that we know is very sparse. So that's the high-level idea. And in the diagram that you see over here, we can see that we have typically a very dense graph, which is highlighted by blue edges. And then we have hidden test edges, which is highlighted by the dotted red lines. And we want to be able to predict these hidden test edges at test time. So again, as I mentioned, this is motivated by this real-world use case where we have graphs in, say, potentially different cities, and we observe them, say, in Montreal and Toronto, and then we want to do this effective link prediction on a new city, in the case of Uber Eats, so say Vancouver. And in this case, that would correspond to recommending users new restaurants to try. Okay, so what is the few-shot meta-learning setup? So the high-level idea is that we want to train a model that can quickly adapt to a new task with less data. In this case, the task is link prediction, and the data corresponds to a specific graph. So for notation purposes, we'll use D as the data set, and that defines the distribution over tasks. By distribution over a set of tasks, I mean just link prediction on each independent graph. And each task has a distribution over data points. So what that essentially means is that if you take one graph in isolation, you can think of like each data point as a collection of the nodes and the edges. So one task corresponds to link prediction in one graph, And at training time, we have a collection of different graphs that we can leverage to then test on a new unseen graph. So that's where the problem really arises. How do we do good on this new unseen graph? So typically, you can think of Fewshot learning in a variety of different settings. So if you take a step back and think of what is Fewshot learning in maybe other domains like images, maybe you'll recall ideas from Metalearning, or the more canonical version of Metalearning that people typically use these days is called model agnostic Metalearning, or MAML. And the high level idea is that you want to learn some set of shared parameters data that we want to essentially use to initialize to a new example or a new task. And these shared set of parameters are typically chosen in such a way that they serve as a very good initialization point for a variety of different tasks, such that if you observe new examples from this new task, you can quickly adapt within a few gradient steps, which is the final equation that you see over here. And I'm not going to go into too much of the detail of the equation, but you want to quickly adapt to this new setting. So but the main takeaway from this slide is that we want to learn the shared parameters data that is effective across multiple different tasks. So just going over how we adapt this meta-learning problem to the graph setting. So the first thing that we have to change is this idea of what is our distribution over. So in this case, we have a distribution over graphs, which means that we're sampling independent graphs from P of G. And each graph is a collection of three things. One of them is a number of nodes it has, so V. Its edge set, E. And for each node, we can also assume that it has some node features. So that's denoted by X. And in this setup, we also can sometimes replace this edge set with an adjacency matrix A. And the main key difference between our setting versus previous setting is that we assume that the training set of edges, eTrain, is substantially smaller than many other previous link prediction tasks. So typically, eTrain is maybe 10% of all possible edges in the graph. So it's a very small, sparse subset. And we want to do effective link prediction when we have very little data. So again, the problem setting for Fewshot link prediction is as follows. We want to have a distribution of our graphs, and we observe a very small subset of these edges, maybe up to 30% maximum. And we want to learn this global link prediction model using these training graphs that it can adapt to a new graph, G star, that is also drawn from the same distribution of our graphs, P of G. So how is this related to traditional meta-learning? So traditional Fewshot classification generally assumes a distribution over tasks. In this case, each task is a graph. And crucially, the difference between our setting and other meta-learning setting is that each graph is non-IID. Because graphs have edges which are connected to different nodes, it inherently makes them non-IID and inherently makes the training much more complicated than other, say, image domains. This is a particular nuance of the graph setting that is not prevalent in other domains. So what's the high-level approach that we're going to take? So what we're going to say is that we're going to learn two models. One of them is a local link prediction model, which is if you give me one graph, say GI, how do I learn parameters that do well on GI? And we'll call these set of parameters psi. And then we're going to learn a global set of parameters called theta that we're going to actually meta-learn to initialize psi. And to do this, we're also going to learn this parametric encoding function, which I'll call the graph signature function, which is essentially going to consume the current graph it's observing and use that to initialize the local link prediction model. And we'll see how these models are trained in a second. But the high-level idea is that we're going to learn two sets of parameters. One is a global parameter that is trained across graphs, and one is a local parameter, which is initialized by the global parameters that is specific to a particular graph. So for the local link prediction model, we can choose any particular model, really. But for the sake of simplicity, we want a robust model that works relatively well without too much engineering. So one such model is the variational graph autoencoder model, which was proposed by Kith and Welling in 2016. But it can be any GNN-based solution. It doesn't have to be this one. So specifically, the local link prediction model consists of two models. One is an encoder, which we call the inference model, Q, and the generative model, which is literally takes the embeddings of the output of the node embeddings and predicts the link using a dot product or a cosine similarity. So the probability of an edge is literally ZU transpose ZV, and you take the sigmoid of that and you normalize that to a probability. Finally, what is the overview of the MetaGraph algorithm? So the MetaGraph algorithm, we use, again, as I mentioned, global parameters data to initialize all the parameters of a local link prediction model. And to do this, we'll learn this thing called a graph signature function, which is using the actual structure of the current graph to actually initialize the parameters of the local link prediction model or the inference network. And crucially, the signature function will be optimized in the outer loop using second-order gradients. So why do we want some graph signature function? We want some way of determining how similar a new test graph is to all the previously observed graphs. So the idea is that during training, we'll observe, say, n graphs from a particular domain, and we want to leverage the shared vector in these graphs to initialize this new graph that we're going to see. So we use the graph signature function to actually initialize this. If you're familiar with hypernetworks, this is very similar to a hypernetwork where we have a neural network initialize the weights of another neural network. So the key idea is that if the test graph we observe is very similar to a training graph, we don't want the learned parameters to differ too much. But if the test graph is very different from the previous training graphs that is observed, we want to kind of shake the weights a little bit, and then so that the new model can actually converge to a new, more optimal setting. So what is the actual form of the graph signature function? So the graph signature function can really be any GCN, and then after a GCN, you can use a small little MLP that gives you like an encoding for the entire graph. You can think of it as a small graph encoder. But the crucial difference is that this graph encoder is essentially a graph encoder for every layer of the new local link prediction model. So the graph signature function outputs modulating parameters for every neural net layer in this local link prediction model. And we'll see what that means in a second. So yeah, sure. Yeah. No worries. So what is so how do we actually define the graph signature function? So typically a graph signature function is as a GNN, as I mentioned. So it has this message function M, which is sending messages between nodes. It has learnable parameters W, and it's any GCN really, or any graph neural net propagation rule. In this case, we use a GCN, but the key characteristic is this message function that is sent across different nodes. So this is one layer of a graph signature, but you can stack this layers multiple times. And the final output is this learned embedding vector that we call the graph encoding. And the key difference is that we learn this encoding vector for every layer of the local link prediction model. So we'll have a separate embedding vector for every layer in the local link prediction model. So there's multiple variants of the graph signature function. I'm not going to go into too much detail here, but some of them have different types of weighting schemes. Some of them have different types of attention schemes. You can find these details in the paper. So again, what is the MetaGraph architecture? So the MetaGraph architecture is as follows. We have a encoding function that takes a graph, and then it gives you parameters mu and sigma, which is for the inference model. And then we learn how to predict links using a dot product decoder. Crucially, the GCN layers of this encoding model are provided to us by this graph signature function, which pre-computes what weights should be here. So this graph signature function is updated in the outer loop of gradient-based meta-learning. So we're doing second-order gradients here. But these GCN layers for the local link prediction model are not updated using second-order gradients. So there's a key difference. So theta corresponds to the graph signature function as well as the encoder. But then we have another set of parameters, psi, which is only the local link prediction model, which is only corresponds to local updates. All right, so the probably one question you might have is how does MetaGraph differ from the canonical mammal? In a small little slide, MetaGraph actually has one additional source of parameterization to the graph signature function. So the graphical model diagram is slightly different. And as a result, we'll see that this addition of this signature function greatly improves performance. So quickly moving on to experiments now. So how do we actually validate if this MetaGraph approach is valuable? For experiments, we pose three different questions. One of them is, how do existing approaches do well in sparse regimes? Does pre-training help? And does MetaGraph actually lead to substantial improvements? And finally, can we get some insight into what this graph signature function is actually learning? So for testing, we use three different data sets. The first one is a biological protein-protein interaction network, PPI. The second one is a robotics 3D point cloud dataset. And finally, the last one is a citation network from academic papers. And they each have different number of graphs, number of nodes, and number of edges, and different number of characteristics. So they're from three different domains, really. So the first question we want to ask is, how do existing approaches do when they have sparse data? And we can see that a lot of the existing approaches, which is sometimes heuristic-based approaches, such as Adami-Gadar, or canonical node embedding based approaches like deep walk, they actually struggle quite a bit when you have only 10 or 20% of edges. And they only take off when you have 60 or 70% of edges over here. So crucially, a lot of these models suffer when you have very little data. So we really wanted to address this issue with MetaGraph. So does pre-training help? So the first question is, or the second question rather, is pre-train. And what I mean by pre-training is that learn the same set of parameters across the training graphs and just adapt them to the new graph using fine-tuning. So there's no second order gradients when I say VGAE plus pre-train in this table. And we find that pre-training does help a little bit, but crucially, it doesn't help a lot. And that kind of makes sense, because as you increase the number of graphs you have in your data set, you have this problem of catastrophic forgetting, where your model tends to forget what it sees in the first place. And we see that it's really hard to adapt to new graphs from this domain. And our final question was, does MetaGraph actually help? Oops. So MetaGraph actually provides substantial benefits. We find that especially in the 10 to 30% regime, which is what it's intended for. So when we have sparse data, we find that MetaGraph actually provides maybe up to 5% benefit just by adding this encoding function that we call the graph signature function. And this is across the board, across 3 different data sets. So indeed, we find that meta-learning in this setting helps quite a bit. And the key difference is that naive meta-learning through MAML isn't as effective. So you do need this graph signature function idea, because it's encoding some sort of inductive biases. So yeah, specifically, MetaGraph provides about 5% improvement over MAML, 5.3% improvement over just regular pre-training, and overall maintains strong performance with up to 10% of the data, which is very surprising, really. So just in plots now. So what I'm showing you now is the plot of the improvement of the local link prediction model with respect to number of gradient steps. So we can see right away that MetaGraph, when you have a graph signature function, shoots up really fast and converges almost to the optimal point within 5 to 10 gradient steps immediately. And this is true for multiple data sets, so PPI as well as this 3D point cloud data set that I alluded to. So finally, the question that we may want to ask is, like, so what is actually being encoded by this graph signature function? So we find that when you plot the Pearson correlation, the graph signature function is actually highly correlated with the node features themselves. So we see almost 90% correlation with node features, and negative correlation with the number of edges between graphs and the number of nodes in different graphs. So it seems that the graph signature function is actually using this node feature matrix quite a bit. So in conclusion, this main algorithm that we introduced called MetaGraph is for this new setting of Fewshotlink prediction, where you only have very sparse data and you want to adapt to new graphs taken from a particular domain. There's a lot of interesting future work that can be done in this space. One of them is understanding how different variations of a graph signature function might help, and perhaps more importantly, whether we can learn a specific metric for actual meta learning to actually evaluate progress better. So with that, I think I'm almost at time, so I'll conclude, and I'll open the floor to questions.
Awesome. Thank you so much for that, Joey. That was a good high-level overview on the paper. The paper is actually quite technical, and if I'm being honest, the first time I read it, there were a lot of things that I didn't quite catch. And that's kind of like the goal of this discussion session, is to sort of bang those details home. So I think a big prerequisite to understanding how MetaGraph actually works is understanding how MAML works, right? So the model-agnostic meta-learning is the fundamental way you train this MetaGraph model. Do you think you could just talk us through a little bit about how that works in terms of the fact that there's a learner and then there's a task-specific learner, and how that correlates to your global learner and your, again, your local learner?
Sure. So MAML, in just a picture, is quite simply, suppose you have different tasks, say 1 to n. You want to learn a global set of parameters data that serve as a good initialization point for any of these tasks. In this diagram, there's 3 tasks. So what I'm showing here is that within a few different gradient steps, we can achieve really good performance on the new task, say phi1, phi2, phi3, which is the local link, in our case, a local model. And so there's 2 sets of parameters: a set of global parameters data, which are quote unquote meta-learned, and then the set of local parameters that are quickly adapted based on the global initialization point data. So learning happens with a few gradient steps. So that's the whole idea of MAML, which is we want to do good learning just by seeing very few examples of the new task because we already have baked in a lot of prior knowledge in this global set of parameters data.
Right.
So
just to clarify that then, so if the data were trained, so thinking of an image problem, if the data were trained on an ImageNet data set where the tasks now are like cat tasks or like, I don't know, chair tasks, would the tasks you learn downstream, so the phi's, would they be samples from that same distribution or would they be out of that?
So I'm kind of missed a little bit because my internet cut off, but just to answer your question from what I understand is, so different tasks correspond to different data sets. So in the case of ImageNet, this would be different subsets of ImageNet. For example, say maybe you have a task of discriminating between cats versus dogs, and maybe another task would be differentiating between chairs versus tables, right?
Right.
So inherently, they're two different. You can build two different data sets from ImageNet from that, right? And then you would have samples from each of these two data sets that you would use to learn data. And the new task could be differentiating between, I don't know, lions and tigers, right? And
Right.
that would be your unseen new task that you want to quickly adapt to, having only observed, say, maybe 10 examples of lions and tigers.
Okay, so those local things you learn are things that are out of the distribution then? Like you haven't seen them before?
Yes, precisely. You haven't seen them before, but it's not entirely correct to say that they're out of the distribution because they're, in this case of ImageNet, they're being drawn from the same overall data set.
Okay.
But you can say that there are different subsets of the data set which have some structural similarities.
Okay. So like if P of G was a distribution of the whole world of all the images, then yes, it would be a subset of that.
Yeah. So in this case, like P of G could be all possible, in the case of, I don't know, robotics, all possible robot arm configurations that we draw like 3D point clouds from.
So then if we convert this now to your graph paper, those specific phi's, those tasks, those are those like the tasks for different data sets? Because you said you trained on or you tested on
Yeah. That's a really good question. So each phi in our setting corresponds to a specific graph taken from this larger P of G. So each task corresponds to doing link prediction on a specific graph. And at test time, we have unseen new graphs taken from P of G.
Okay, gotcha. That was a little hazy for me. Cool. The actual algorithm is quite meaty, so I was wondering if we could go through it because you have a good diagram of it in the paper, and also we clipped it into your slides. So I was wondering if we could walk through this just a little bit into more detail to bang home those details. So if we start just from line 1, so here every G in the batch of G would be all the graphs across these 3 data sets, and you're pulling samples from each one of them. Is that correct?
No, that's not entirely correct. So these 3 data sets are distinct. So each data set has, say, 100 graphs, right? And and we're taking a batch of graphs from 100 graphs. So these 3 data sets are distinct. So for example, if I'm doing Metalearning for, I don't know, prediction of 3D point cloud data in robotics, right? I would have only graphs that have 3D point cloud data. And we sample one such graph for each G in G batch, which is line 1. And so the inherent question that we're trying to answer is that given a specific domain where these graphs are coming from, so in the case of 3D point cloud data, all graphs are 3D point clouds, can we leverage structural similarities across these graphs to inform link prediction for a new graph also taken from the same domain?
Okay, interesting. Okay, so it is specific to the domain, and you sample some graphs that should be in that domain.
That's correct.
Okay, and so we split it up into train, validation, and test as we normally would. And now I guess this is the meat of it. We get in line 3, we get into the graph signature function. In your work, you guys proposed 3 different ways to go through to actually train with these train edges in your graph signature function. But the output of SG would be an overall graph embedding. Is that right?
I think that's very close to being right. So SG is actually it is a graph embedding, but specifically it's a graph embedding for every layer of a GNN in this local model. So if my local GNN had 3 models, I would get 3 embeddings, 1 for each layer.
Okay, but you sum that up into one vector at the end.
No. You don't sum that up into one vector.
Okay.
So the idea of graph signature is that we want to modulate the weights of each independent layer of my downstream GNN, which is the encoder, right? So each layer's GNN has a corresponding quote-unquote graph embedding vector, which I'm using the term very liberally. So this graph embedding vector determines the weights of the specific GNN's layer. So if I have 3 layers in my GNN, I have 3 corresponding graph embedding vectors that I use to, I don't know, maybe the easiest thing you could do is like do a element-wise multiplication with this graph embedding vector and this matrix, and I will determine the layers of my downstream GNN.
Oh, okay, understood. So these will correspond to the local layer. So they're essentially the starting point.
Exactly. So we initialize these local layers using this signature function.
Okay, cool. So that's what we do in step 4. And now I guess like lines 5 through 9, these are this is the few-shot learning part, right? So these Ks now are a hyperparameter of the number of things you actually train on?
Correct. So this is now where the local link prediction model takes over. So after we initialize phi, so at step 0, we update the local link prediction model using the canonical variational graph autoencoder loss, which corresponds to, which is, if you're familiar with VAE, this is just the regular elbow, just modified to the graph setting. And then we learn these parameters phi with k gradient steps, but crucially, what we don't learn is the graph signature function here. So we have a stop gradient operation in line 6. So the graph signature function is never specific to a given graph. We want the graph signature function to encode global graph properties, so we don't update it over here. We only update it from lines 10 to 14. So in lines 10 to 14 is the outer loop of Metalearning, where we update the graph signature function as well as the global parameters theta using the parameters phi.
Okay, gotcha. So if we just go back to line 10 then, so we take the local parameters to put back into the global, because at the first step you have nothing there. Those are random parameters for the graph signature function. Okay, and then we compute. So
one key distinguishing point is that the parameters phi are being put back into parameters theta, which is like, you can think of it as having 2 different VGAE models, and the graph signature function is separate from that. So phi is being initialized back to another VGAE model, which is acting like the global VGAE model.
Okay,
if that makes sense.
Yeah, definitely. Actually, just a question while we're here. Somebody wants to know, or it's Willie that wants to know, how intensive is this training process? Do you have to, like, how much RAM does it take, or that sort of thing?
So compared to regular training, because we're using second order gradients, obviously it's much more intensive. So specifically, that depends on the size of your graphs, really. So I mean, if I have to give a ballpark number, it's maybe 2 to 4 times slower than regular training, because it's using second order gradients to update everything. But the idea is that when you give me a new graph, right, at inference time, it's very fast because it can quickly adapt. So that's the whole basis for this formulation, that we want to do well at test time.
Okay, and training takes longer because now we have a second, or we have to compute the derivative twice, essentially.
Yeah.
Okay, just on that note, so we are computing derivatives only on the validation set, right? Not on the train. The train set is there to initialize the global parameters.
Yeah. So the train set is there to initialize the global. I mean, so the train set is there to update the local link prediction model. But when you want to do the global update, we use the validation set of edges. But implicitly, because we're using phi of k, which is trained on the local model, our trained model has knowledge of the training set of edges as well, if that makes sense. But we are only using the validation set to update the global model. Yes, you're correct.
Okay, so what about the local model then? We also use the validation set there?
No, we don't use the validation set to update the local model. We only use it for like actual validation purposes.
Okay, right. That was my next question. So then to actually do validation and hyperparameter tuning, it's like quote unquote legal to use the validation set.
Yeah, so there's one important distinction that's perhaps maybe wasn't clear in the talk, is that there's 2 different hierarchies of validation here. One of them is that if you have a data set of graphs, you can use a certain set of graphs for training, and you can have a certain set of graphs for testing and validation. So when we do validation for MetaGraph, we're using this held out set of graphs to actually evaluate the performance for the global model. And then the other underlying level of hierarchy, or lower level, is that you can have training splits within edges. So this is particular to a specific graph now. So there's a graph level split, and then there's like a data set level split as well.
Okay. Oh, that makes more sense. Okay. And just checking through some questions. I guess reflecting a little bit on line 3. So we don't actually compute any gradients here for the graph signature function. So what was the motivation then to use it?
Yeah, so the motivation to use the graph signature function is really we want to be able to like leverage similar structures between graphs when we see a new graph. So the idea is that if I've seen, like, if I take like intuitively, if I see a social network, say such as Twitter, and I'm following 10 different people, it's likely I'm friends with them on Facebook as well, right? So there's some inherent similarities that are there, even though they're two different social network platforms. So how do we leverage this inherent graph structure when I want to do good prediction on a new graph? So this graph function is attempting to encode this structural properties into a vector that we will use to initialize the weights of this new model, if that makes sense.
Yeah. So then you said that if it's if on test time you encounter a graph you've never seen before, you want to sort of shake up those shake up the weights such that it's at a better initialization. I think you said something to that effect.
Yeah. So because the graph signature function quote unquote modulates the parameters of the local link prediction model, so what it ends up doing is that if we compute this graph signature for this new graph, and it turns out this graph signature is very different than the ones that we previously observed, then we'll more aggressively change the weights of the local link prediction model. So we'll change them by a lot. But if it's very similar to a graph that we've already seen before, we don't want to change the model parameters a lot because they're already close to optimal. So we're not going to quote unquote shake the weights quite a bit.
Okay, and this whole process would happen in those 3 different ways that you do the modulation.
That's correct.
Okay, cool. So I think you had a slide about this. It was quite interesting about what the graph signature function actually encodes, right? I think you found that it's very similar to node features. And we have a question from Amir who's asking, is that the desired outcome, that it's more that it learns node features or more on structure? And you kind of touched on this already.
I mean, so the desired outcome is whatever. So the graph signature function will learn whatever is most useful to do global link prediction, right? So we can interpret it by saying that we want it to learn structure, but like we don't want to enforce these biases during the learning process. So we expect it to learn whatever is most useful. Sometimes that's structure, sometimes that's node features. And it turns out, so the reason it learns effective node features more so than specific structural elements is that when you have a lot of sparse data, you're already breaking a lot of the structure in the graph. Right. So to do effective link prediction, you have to use the most salient signal, and a lot of the time that's just node features. So in some sense, it makes a lot of sense why it's leveraging node features more than structure, because you're already breaking a lot of structure.
Right.
In the sparse setting.
But I wonder then, how do you think that would perform in like the multi-edge case, or if you have a heterogeneous set, then like it would be hard to bang down that 2 node features. It has the opportunity to learn saliency to a lot of different things then.
Right. So the multi-edge or multi-relation setting is quite interesting because there are some other different approaches to do meta learning there, and specifically in that setting, the problem is usually formulated slightly differently. Where what you want to do is like you want to generalize to a new relation type, so a new type of edge, given only few examples from that edge. So in this case, the MetaGraph algorithm in its current formulation would not be equipped to handle that because we don't actually use anything from different types of edges, and specifically we assume simple graphs. But you could possibly extend this by having a different type of GNN as a signature function that actually incorporates a different edge type. So for example, if I use an RGCN as opposed to regular GCN in the graph signature function, that's one cheap way of handling this multi-edge setting.
Okay. Okay, and on that note, I guess you guys said that it wouldn't be hard to switch out the variational graph autoencoder for something else, and if it like I don't know GAT or something or GCN, and so if it was the heterogeneous case, would you be able to switch it out as easily with another type of heterogeneous layer?
So I just want to quickly clarify 2 points that you've brought up. So one of them is that we can easily switch out the model. So the VJE model actually has GAT layers or GCN layers. You can choose layers. So the encoding function at VJE can be anything you want it to be. So by switching out the model, I mean switching out the loss function.
Okay.
Yeah. So you can be a more complicated link prediction model. So in that case, we are already accommodating like GAT level networks or GCN level networks.
Okay.
Yeah.
And so then in the heterogeneous case where you have different types of nodes, since we're already using GAT, I guess there could be like different types of gap that accommodate for the heterogeneous case, would that just be an easy switch out of the layer?
It depends,
Do you foresee
right?
problems with that?
I mean, so it's hard to say. Like, I mean, so the only thing that the graph signature function learns is an embedding or like this modulating parameter that effectively initializes a new layer in this encoding model, right? So as long as your signature function can actually accommodate multi node labels, you should be able to learn this parameter initialization point for whatever downstream encoder decoder architecture you use. So the choice is really with the practitioner. They can pick whatever model that you want to use for the graph signature function, and that could be as simple as an MLP or as complicated as the most complicated GCN layer. So in practice, you have a lot of flexibility with what you choose.
Okay, fair enough. So I think now that we've kind of know a little bit about the algorithm, I thought it would be interesting to bring up the distinction between certain things. Like there is a distinction between pre-training and meta-learning. And I looked at one of your reviews in OpenReviewNet, and somebody said transfer learning. And there is a distinction between all three of them, right? Could you touch on those a little bit?
Yeah. So a lot of the time, there's many of these terms that are used in the literature, and then it's easy to conflate all of them. So transfer learning is this global task where you want to leverage prior information to do well on an unseen new task. There's multiple ways of doing transfer learning. Meta-learning is one such way. Pre-training is another such way. So pre-training in our setting corresponds to using past data to learn some set of parameters. So whenever you have neural network models, you can pre-train them because you can pre-train the parameters on existing graphs, but this is not always true for other link prediction approaches. So classical link prediction approaches like Adamic-Adar that use statistical properties of a given graph are inherently transductive. That means they only operate on a specific graph. They can't leverage information from other graphs in its history. So GNN-based approaches are quote-unquote inductive in the sense that they can generalize to new graphs because we're learning these set of parameters. So by pre-training, I mean learning a set of parameters such as the global initialization point theta over previous graphs that it has observed, and fine-tuning corresponds to when I give you a new graph, adapting these parameters, whether that's through second-order gradients or just typical, just normal gradients. Fine-tuning corresponds to adapting the old set of parameters that are pre-trained to this new domain or task. And meta-learning is a specific way of doing fine-tuning where we're essentially learning how to learn, and the way we learn the pre-training weights is through second-order gradients.
Okay,
and it's important to note that there's multiple types of meta-learning, and we're specifically focusing on gradient-based meta-learning.
Oh, okay. I didn't realize there were other ones. So what I know. Okay, so fine-tuning then, is that synonymous to fast adaptation? You had a slide on it on your results.
Fine-tuning is not as synonymous to fast adaptation in the sense that fast adaptation corresponds to learning with very few gradients, but fine-tuning can sometimes take many gradients. So fine-tuning just means like adapting, so changing your current set of parameters a little bit to the new task. That could take many different layers of optimization. Fast adaptation specifically corresponds to the scenario where you want to fine-tune when as few gradient steps as possible.
Okay. So if you could go back to your slide, that slide had, I think, was it one gradient that it took? No, a little further.
Okay.
It was one of your results slides.
Results slides. Okay. Maybe this one.
Yeah. Actually, maybe the next one. Or yeah, these all work the same. So you compared here with fine-tune, no fine-tune. I wasn't sure what graph sig was, and we all know what mammal is now.
So graph signature is the MetaGraph version with a specific graph signature function. So graph sig is our approach. Mammal corresponds to the same algorithm when you remove graph signature. So the idea is to see how well does this vanilla mammal work. No fine-tuning means when I'm in the transductive setting where I only evaluate on the test graphs and I don't use my previous training graphs. So if I just do the regular VGA model only on the test graphs and I average the performance, fine-tune means I get to use my previous history of training graphs to inform my new prediction model on the test graphs.
Okay, makes sense why fine-tuning beats no fine-tuning. And it's cool that GraphSig is beating mammal because now that inductive bias from the structure is actually helping you learn.
That's correct.
On sparse data. Very cool. I think those are pretty foundational questions that I asked you that I think now maybe we all understand the paper a little bit better. But when I first read it, I was like, okay, link prediction. The only link prediction method I know is seal. And yes, you can use embedding-based methods to do link prediction. But I was wondering, did you guys try seal for link prediction and for this task on sparse data? And what was your feeling on it?
So we didn't try seal specifically, but we did try a variety of different other link prediction, and more of the details are in the paper. But specifically, we tried the most representative classical method, which is Adamic Adar, which just specifically uses neighborhood characteristics of a node to determine the likelihood of an edge existing. And we used a canonical deep learning method in deep walk, which is does random walks on your graph and uses the node embeddings crafted from these random walks to determine the likelihood of a edge. We also use just regular NLP to see what if we remove the graph structure completely? What happens then? And it turns out it doesn't do as well. So you do need a little bit of graph structure. And then we obviously tried our method, which is builds on top of the VJE model. So those were our main points of comparison. And really, we wanted to highlight the different ways of doing link prediction rather than specific algorithmic or architectural differences.
Okay. And I guess, so you guys landed on the VGAE as the most robust method. Do you think that's because of the generator part of it? Because if you were to...
So the VGAE model is not the best link prediction model by any stretch of the imagination, but it's also, there's two reasons we picked VGAE. One of them is because it's such a simple model. And B, it's kind of robust to many different things because it has this regularization term. If I go back to the algorithm, which is my last slide. I'm going the wrong way. The VG has this other regularization term which prevents overfitting, kind of, and this is particularly important when you have this data set of graphs. When you're doing this over multiple graphs, this prevents overfitting to any one specific graph. We found that this helps quite a bit.
Okay.
Yeah.
So even if you were to swap out the layer, you still, having that KL divergence there was really beneficial in the long run.
Empirically, we found that to be beneficial, yes.
Okay, cool. I guess I'm going to do a last call for the audience. If you guys have any more questions, please post them in the chat. But maybe just a last question for you, Joey, while we're waiting for that. This is not a pain point. I was just genuinely curious. One of your reviewers' comments were that you guys did not compare with Transy or Rotate or neural tensor factorization. But I'm not a graph person, I'm not a graph expert, so I looked those up, and those are knowledge-based.
The reviewer was misinformed in that setting because those are specific to graphs that have multiple different edge types or relation types, and those are knowledge graphs. So typically, a lot of the link prediction problems are in that setting. So I can see why the reviewer was confused. But our problem setting is completely distinct from that. We're assuming only a single edge type, so simple graphs. So this MetaGraph in its current iteration would not work in those settings, but you can, as we talked about earlier, you can adapt MetaGraph to incorporate multiple edge types to do possible link prediction there. But that's not the intended goal of MetaGraph. We want to do good link prediction in sparse settings, and that's independent of if you have different edge types or not.
Okay, but in the most simplest sense, if you had a normal graph that wasn't super sparse, would the most normal baseline to compare it be seal or embedding-based methods?
I would say embedding-based methods because that's the most representative model.
Okay, fair enough. So I think the audience is done, but I was just wondering if the next step, would it be to make it more heterogeneous, or would you guys?
I think that's a very interesting next step, adapting them to more heterogeneous graphs. But I also think that's a very obvious next step, right? And it's a pretty low-hanging fruit. I would be more interested in learning a metric to compare graphs. So for example, this graph signature function is kind of implicitly doing that. So we're saying that how similar is this test graph to previous graphs, but it doesn't actually give you a quantifiable number saying that says, oh, this graph is 80% similar to the previous graph I'm comparing with, right? So having this notion of a metric, even if it's an approximate metric, because graph matching is an NP-hard problem. So having this approximate metric where you, instead of giving only one graph in, so if I look at line 3, for example, and the graph signature, it's only taking in the current graph. But if I give it a pair of graphs, and I can say, actually, this graph is this much similar to this other graph, I can then use that information much more creatively to inform the actual local link prediction model and say, use information from this graph in this data set more so than this other graph in this data set. So you can do something like an attention over all graphs in your data set and say, graph number 10 is most similar to the current graph I'm observing. So let's use structures or information from that graph more so than structures and information from other graphs.
Oh, okay. So you would build upon the graph structure from, like, because the graph structure embedding already told you a little bit about how they relate to other graphs, but it's not an overall score, you mean?
Yeah, so like learning a metric specifically I find would actually help quite a bit, because when you have a lot of different graphs, this graph signature function can get oversaturated sometimes. So to get better signal to noise ratio in some sense, we want to only focus on the graphs that are the most representative of the current graph you're observing.
Okay.
So one way of doing that is to have this this metric and then using attention to actually modulate the gradients better.
Oh, that would be interesting. We actually have a last question from the audience, Joey. Amir wants to know if you have any thoughts on how much sparsity makes this more method preferable to other alternatives. I think your paper touches on it, but do you want to add anything to that question?
So sparsity is really an empirical phenomenon, and that's really dependent on the domain you're in, right? Some domains, sparse data could mean 10% of edges, while other domains, sparse data could mean 50% of edges, right? It's often an empirical question, but we found that usually current link prediction methods outside of MetaGraph, they have more than 50% of edges, and that's where they usually operate. Most of the time, they use 70% of edges for training. So in practice, we see the most benefits from MetaGraph at around 10 to 20% of edges, and the 3 different domains that we tried. But obviously, if it's a completely new domain, that number could possibly change. But I don't think it will be more than 50% at all.
Okay, fair enough. Great. So that's about the end of all the audience questions. I want to thank you so much for coming on the spotlight and sharing with us this really cool paper. Just for me personally, I think I would like to I know you have code out, but I would love to try it out on other real world data sets that I have that are also super sparse, and that's why I was really attracted to this paper. So thanks so much, Joey. If you guys are interested in the slides, they're going to be up on ai.science, so check them out after this talk. Thanks again.
Cheers.